I look a little bit like John, but not that much like him. So we're going to start the last session, 40 minutes. I know, tell you.
Thank you. So it's good to present our project titled Estimating Nonlinear Heterogeneization Models with Neural Networks here. And it's joint work with Leonardo and Matthias Rockner. We all work for central banks or have worked for central banks. So there's a disclaimer. So the views in this presentation are probably those of the authors. And one of those views is that macroeconomic models of the future will incorporate features like heterogeneizations, who basically respect risk, as well as aggregate uncertainty and aggregate nonlinearities. Because these models, they help us study very interesting questions about how social inequality matters for the dynamics of the economy, as well as how aggregate policies shape income and wealth distribution. The problem with working with those kinds of models is that they're really difficult to solve because elevated complexity that we have introduced, and because they're difficult to solve, they're even more difficult to estimate, because usually we need to be able to repeatedly solve those types of models if we want to estimate. So what we do in this paper is we develop an estimation procedure that's based on neural networks, and then we apply it to different models, but one of them will be fully nonlinear heterogeneization New-Bayesian model. So to be able to do this estimation procedure that we have in mind, or to accomplish this task, we introduced two key innovations that tackle different estimation bottlenecks. So the first one we call extended neural network, and this one allows us to avoid this repeated solving of the model. The second one we call neural network-based particle filter, and this will reduce dramatically the cost of likelihood evaluations. So I will talk about them, of course, in more detail. So first, about this extended neural network. So it's easier to explain if I start from the solution procedure that we all are familiar by now, that we use to solve those economic models with deep neural networks. And basically, these are the 4 steps. So step 0, if you have a heterogeneization model, you have to somehow keep track of the distribution of agents. So what we will do and what we're building on in these approaches, they use just empirical distribution of L agents to keep track of it. Then we will parameterize individual and aggregate policy functions with deep neural networks. And then we'll construct a loss function, which is usually some sort of weighted mean of squared residuals of different multiple gradients. And then we train those deep neural networks using some sort of stochastic optimization process, in which we try to minimize the loss that we constructed in point 2 over the points that we draw from the state space. And we get those points usually by simulating the model forward. And this ensures that we kind of end up solving the model in the relevant region. But we can't really use this approach for estimation, or at least it would be very, very costly, because training those neural networks, it takes time. We can't do it like sufficiently often if we want to do estimation. So our extended neural network idea allows us exactly to avoid this repeated solving. And to do that, we basically modify the step 1 and step 3 here. So the idea is to treat some of the parameters of the model that we're interested in estimating as additional dimensions or additional sort of pseudo-state variables of the model. So basically exploiting the fact that neural networks are really good at approximating high-dimensional functions. So adding a few extra dimensions should be doable. And then during the training, what we also do is from time to time we will throw new parameter values. So when the network has trained, it doesn't only give us the sort of optimal policy functions for a particular parameter combination, but over different parameter ranges for multiple different parameters. So the problem we have created is a more complex one. So it takes, of course, a little longer to train this kind of extended neural network than just to solve it for a particular parameter combination. But the good thing is that we only have to really do it once. And by once, I mean, like, I have done it. I could share the network weights with you, and then, you know, you never have to basically solve this model yourself again. You would just to, you know, evaluate those neural networks. And this is one of the, like, very simple example of the output from this neural network. So this one neural network will give us, you know, policy functions for different parameter values. There's different parameter values and different lines, and on the x-axis we have different state values. And although there are like 3 lines here, of course it's going to be like a surface or a continuum. So at first we thought this is enough. Now we are not repeatedly solving the model. We should be able to do that quickly. But since we're working with nonlinear models, calculating the likelihood of the model, you typically do it with some sort of Monte Carlo filter, particle filter. And although evaluating those neural networks for just one particle is of course like cheap and quick, once you start doing it for thousands of particles and perhaps hundreds of time periods, this really adds up. So this particle filter, just running it takes, you know, seconds to calculate a single likelihood variation of the model. So we introduced something called neural network-based particle filter, which is essentially like a surrogate model for the particle filter over the parameter ranges that we are interested in estimating the model. The procedure that we do is a really simple standard sort of machine learning exercise that you find in all those machine learning frameworks tutorials. It's just we use this particle filter to create a data set, and this data set will have parameter values and just all the log likelihoods that the particle filter produces. And then, well, we can split this data set into training and validation samples. And then on the training sample, we can fit another neural network. And we can use this the validation sample that we kind of left out to check for overfitting and so on, to adjust this in training. So in the end, we will end up with a neural network that gives us directly the mapping from parameter values to model log likelihoods. So we're for the next steps that come, like running the Metropolis Hastings algorithm, we will no longer be, you know, evaluating the particle filter, but we'll just evaluate this neural network based on particle filter.
Can I ask you a question? So, like, in fact, 2 questions. So, like, probably we'll answer them later, so feel free to postpone that. But the first one is, you know, like we had talked over the last few days. So, like, how will, if you have a lot of parameters, despite you have like surrogate, you know, to simulate from, we need probably a lot of draws from parameter space. So like
so yes.
And then so let me just finish it. Then the second one is you essentially then afterwards you want to use the surrogate for this, you know, from your simulations essentially, right? What is the intellectual data to use to ensure that the second service is good enough?
Second service is good.
So you said you do 2 surrogates, right? You do one is just like essentially one solution.
So the first one, we don't really call it like a surrogate because it's neural networks approximating the voice functions for
states and
parameters. Yes.
That's a surrogate.
Okay.
Anyway, no, but
yeah.
you have 2 things you interpolate on. You have a solution that you have an interpolant of your solution, right? This is an error.
Okay.
Yeah, it has. And
yes.
When you generate something on top of that, this will have an error too.
Yes.
Or based on something that.
So we will have like it's a very good question. We don't have like a full answer. We have a comparison for a simpler model where we can do, standard solution methods. We have a rank model where we can do time iteration and without the particle filter neural network estimation, and we have comparison. So, but it's a good question. And regarding the first point, yes, you have to draw a lot of points from the parameter space, so you can alleviate this problem by not drawing like from uniform, random uniform, but like some sort of solval sequence or something like that. A little bit. The other thing that's nice about this is it's completely parallelizable, this particle filter. So you don't have to run it in sequence. You could parallelize it over, several GPUs if you wanted to. So in the end, yes, it gets more difficult the more parameters you have, because dimensionality grows and covering those parameter spaces, it's more and more hard. But at least you can also scale the hardware with it very nicely. And the other thing that's nice is it tends to also smooth out some of the noise in particle filter. And this is the next slide, and which means that you could use like more rough, let's say, particle filter, because the next step will also smooth out some of the noise. And that means that you need fewer particles. You can do, generate a bigger data set or do it faster. But thank you for your questions. It's very relevant. And yeah, this graph is actually exactly illustrating this last point that I was making. So on the x-axis we have this parameter, and on y we have this small level of likelihood or whatever the particle filter spits out. And each of those little orange dots is the output from the particle filter, and the blue line is the neural network fits. And of course, this is just for one parameter because it's easy to plot, but in principle, we do similar approach for multiple parameters. So just a quick recap before I show you some applications. So we have those two key innovations. The first one we call the extended neural network. And this one allows us to avoid this repeated solving of the model. And then the second one is dealing with this bottleneck of the particle filter. We call it neural network particle filter, and it allows us to do very fast likelihood evaluations after certain term. And now I would like to go through some applications. So I have basically three. So the first one is a really simple three-equation NK model where we have an solution, and that's just to illustrate that this extended neural network can match the true solution. The second one is a simple rank model that I also mentioned before in my answer to Sam. And this is to illustrate that really the procedure and pair procedure kind of work. It produces similar estimates to the ones that we get without using any neural networks. And then finally, we want to also show that this stuff scales up to fully nonlinear rank models. Yes, there was a question.
So thanks. I think it's a really fascinating idea to start to estimate like this. But just to make sure I understand. So what you're doing is you're basically solving the neural network for solving the model for a wide range of parameters, right? You could say for a grid of parameters, and then potentially interpolate between those different realizations.
Yes, the interpolation is within the neural network.
Exactly. Now, my question is, to me, this reminds me of, like saying, okay, I do a grid, or I do a grid, and wouldn't it be using more information if I had a gradient descent and then just because the evaluation of the model, the solving of the model, right, the function evaluation is very costly. So in a sense, it looks to me that you're creating this big lookup table first, where instead if I said, okay, I do my optimization, and whenever I compute the point, of course, I store it, so that for that parameter combination, I don't have to resolve again. But doesn't that sound like it would be much fewer function evaluations and therefore much faster?
So I think actually we are doing something like the neural network is storing, in principle, the solution for different parameter values, right? That's the kind of idea that during the training procedure, we're not only exploring the state space, but also the parameter space. So and the second part, yeah, that's like part one was the extended neural network. The second part is just tackling the problem that calculating the likelihood is just expensive. Yes. Thank you. Yeah, so the first one, so we have this very simple linearized MK model. So we have analytic solution curve, and the steps we have to go through are like before, but no step 0 because it's a representative agent model. We don't have to worry about how to represent the distribution of agents because there's one agent. So we parameterize policy functions with deep neural network. So there will be one neural network that takes the state and all the 8 parameters we're interested in estimating, and it gives us those two outputs, which is output cap and inflation. And we construct the loss function. So if I go, once more back, and you look at the model equations, first 2 lines, and I go one slide forward, then you see where the errors are coming from that we use for our loss function. The loss function will be weighted, means squared error, as usual. And the P here is the patch size. So you can think about it as kind of parallel worlds. And then we train this deep neural network using stochastic optimization. And we use patch size 500, so 500 parallel worlds. Each of them can have different state realizations, but also different parameters. And we train it for 100,000 iterations in this case. And during each iteration, basically, we draw parameters from this bounded parameter space that we think is interesting. We draw the parameters, we simulate the model, or draw the points from the state space. So here you could, in principle, draw them directly, but to make it kind of more similar to what we do in the end, we're doing it sort of like a simulation way here. We compute the loss, and then we use gradient-based optimizer to adjust the weights to neural network. So in the end, the neural network will start approximating the sort of correct policy functions better and better over this training period. And not only for just a single parameter combination, but over those parameter ranges that I listed here. So yes.
I think I asked you this before, but I'm just asking again to be present because now it's more complete. So when we draw a new parameter, right? Then there will be a different relevant region of the state space. So then how exactly does it work?
Yeah, so basically we draw new parameters to simulate the model forward, and usually after drawing the parameter combination, we do a little bit longer simulation step. We might keep this parameter for the next 10 iterations, and between those 10 iterations, just to create like a new draws from the state space, we do again simulations. Let's say less steps, 10 steps or so on. But the first simulation is a little bit longer, exactly to bring us into this region where those parameters would imply this model to kind of live.
But we would also need to train on this transition states, right? Because otherwise we didn't get the transition right.
So it depends, right? If you're interested in doing the transitions, yes. But if you're doing estimations, I'm not pretty sure if you're interested. The other thing is, it might be that it generalizes well enough.
Right. So
you can get very nice transitions, but this is something we haven't explored. Yes. And this is basically to illustrate that yes, we can basically recover the analytical solutions. So the true solution is the red dashed line. And behind that, you can see this neural network-based solution. And this is only for the equation. The plots for basically output cap, they will look very similar. So the second comparison that we have is a very simple rank model. There's only a reference shock, but it's a nonlinear model. It has zero lower bound, constraint on the monetary policy, and it's simple enough to solve an estimate with standard solution procedure. And the exercise we do is we use the model to create time series of output growth, inflation, and interest rate, and then we basically forget some parameters, and then we try to recover it from the simulated data. And we do two versions. One is with the standard approach, and the other one is with this extended neural network and neural network-based artificial approach. And if you look at the orange color columns, then they are quite close. And this is kind of sort of posterior functions, and they also kind of look quite close. There's a little sort of appendix of the paper where we also explore what happens if there's no solution, but it's, I think I don't have time for it. So, so hopefully these first two things fulfill their purpose. So basically illustrating that indeed this extended neural network can match the true solution, so it's kind of accurate solution method to solve them all over the parameter ranges. And the second one was to kind of convince you that indeed it's not so much different from what we would get from a standard solution method. And what we do in the paper next is we estimate the nonlinear Hank model. And something that we did recently, and only for a few parameters, is to use aggregate time series data for the US. And I will show you some results from that exercise. But we also have similar exercise to the point 2 for the Hank model, where we use simulated data and we try to recover more parameters, like 12 or 13. Just to give you an idea about the kind of sizes that are type of model that we're working with, it's rather similar to what Hedges was presenting yesterday morning. A little bit more complex, so we have a little bit more aggregate shocks, I think. But the household size is very similar. The utility function is a little bit different, but there's also parameter constraint and idiosyncratic risk and so on. We have 3 aggregate shocks. We have one for preferences, one for growth rate, and one for monetary policy, and then we have the aggregate non-linearity. It's one of the place rule. The Taylor rule is constrained by zero lower bound, and we are using US time series data for estimation from 1984 to 2019, and we have constrained ourselves to just use the very basic 3 time series. So this is what the measurement equation can do. And for priors, basically we use fairly loose sort of truncated normal here, because we could use something else, but it was easy to implement, so, or was already implemented, so we were very tempted to just stick with it. But in principle, whatever truncated prior you want, you can use it. So again, just it's a bit repetitive, but I guess it serves its purpose. So here, to train this extended neural network, we go through those steps again. So for this particular model, we are keeping track of 100 agents. And the policy functions are parameterized by deep neural networks. So here we have 2 policy functions. One is for aggregate variables that gives us inflation and wage, and then the individual one that gives us labor choice. And the loss function is essentially a weighted sum of squared residuals of different model equations. Fisher-Burmeister to kind of account for the household optimization problem, as well as the integral power limit, Newton and Phillips curve error, and then 2 market clearing errors. And technically we are also using market clearing errors for the next period, but that's optional, let's say. And then we train this deep neural network, and we do it in 2 steps here. So this is also something that we recently added. So if you remember this Taylor rule, right? then this monetary policy reacts to deviations from this deterministic steady state, but we don't have analytical formula for this deterministic steady state, so we have to kind of compute those values. So the very first step in our extended neural network training is actually solving sort of a model without aggregate shocks, sort of Pythagoras type stuff. And there we have one more network that basically spits out the interest rate, the deterministic steady state interest rate, as well as the output of the deterministic steady state. And we also have, well, that's basically, yeah, we need the two networks, the sort of TSS network and this individual network that still uses the labor choice. And slightly different loss function also, because some of the NKPC doesn't really make sense in that context. And then once it's trained, then we have the full nonlinear Hank model, where we add this well, there we will have individual network as well as sort of aggregate network. You know, like before it, the aggregate network gives us the inflation wage, and we keep this DSS network fixed. So we need it just as an input for the data rule. And to start off the training, we're actually doing something that you could call transfer learning. So we're bringing over the sort of individual or this household network from the first step and using it as a kind of good starting point for the second step. And the other cool thing that we do that's a little bit related to what Marlon was doing is what we call like a curriculum training. So we're making the problem, you know, more complex all the time. So we used to do it from going to rank to Hank with CLD, and now thanks to this first step, we have very good tests for the individual policy functions, so we can go basically from just Hank to kind of nonlinear Hank, introducing the aggregate nonlinearity to CLD over time. So this is pretty much necessary to make the training more stable. Yeah.
Like I'm a bit wondering, like how does you have this finite amount of agents? How does the deterministic steady state work, right? Because individual uncertainty doesn't wash out with the.
Yeah. So it depends on your parameterization. If you have a lot of idiosyncratic uncertainty in the model, it tends to result in quite a bit of aggregate uncertainty. Yes. In our, the range of parameters that we say in the sigma s, the idiosyncratic volatility, that's still like small enough. But once we tried to kind of push it, we saw that it's a potential problem. So you would have to push the number of agents higher, and there you could use the deep ham or the symmetry kind of ideas of kind of using kind of moments, so it would make the input to the neural networks smaller, so you could in the end do a larger problem. Like instead of 100 agents, you could do 1,000 agents. The other thing, like right now, yes, with our current strategy, we can do perhaps 500. With the exploiting symmetries idea, we can push it to 1,000, and we have some more ideas. So hopefully we will be able to push it to the point where we can incorporate a lot of kind of idiosyncratic uncertainty, and it would not cause problems. Yes. So this is like pretty much illustration for the point 3.8. So what we get out of this deterministic steady state network. And here on the x-axis, I will have the sigma s, the amount of idiosyncratic volatility. How much that? 10. Okay, good. And what you can see is that if we increase this idiosyncratic uncertainty, then the interest rate will go down, or the model in which there's more idiosyncratic volatility, right? There's more motivation for precaution saving. The interest rate is lower, and the other output in our model will be higher. And this 3.b is to illustrate what we get out of the second step, where we have the full-blown nonlinear heterogeneous agent models. These are the aggregate quality functions, and you can see that our neural network approach, it can capture the nonlinearity, the kink that comes from the zero lower bound, and those different lines, they correspond to different levels of idiosyncratic uncertainty in the model. So you can see that there's this interaction between the idiosyncratic risk and how the aggregate quality functions look like. So that was the first part about basically now we have, once we have done this, we have trained the extended neural network part, and now what follows is the second part, this neural network based particle filter part. Yes.
Really quickly before we go to the estimation. So obviously it's very great if you can add those parameters to the sentence, but like there must be a cost that it couldn't be for free. So can you just tell us very like vaguely, does for example the solution accuracy somehow deteriorate if you have more, or you can just make up for it by training longer?
You can make up for it by training longer.
Okay, great.
So we have done a little bit of comparison in terms of shutting down those parameter ranges for some parameters, and typically it's the accuracy is very close. It might be slightly worse, but I guess we are also impatient. We right now can train those neural networks in 4 hours. That's the first part. If we would use a bigger hammer and more time, then I'm sure we could try it even lower. So this brings me to the second part, this kind of where the estimation part really starts. So first we need to train this neural network based particle filter, and the steps are the same that I explained before, that we draw the parameters from some sort of your favorite low discrepancy pseudo-random number generator. We use a shuffled or subtle sequence because it was implemented in PyTorch, and it's one of the best that you could use. And then we use this particle filter to calculate the model out likelihood, and then we fit a neural network that basically does the mapping from parameters to model likelihood. And this is actually a very inexpensive step. You can do it in 10-15 minutes on a CPU, because the data set you end up generating is not that large, and yeah, this is a simple step. And the second round, you want to sample the posterior. So what we are using here is random walk metropolis hastings algorithm. You could potentially use something else, but this thing is also very very cheap to do, because we're using the surrogate model to get the likelihood. This literally takes us 3 milliseconds or so. So we can run like really long metropolis hastings chains. And yeah, it's cheap because more or less all the computational cost has been front-loaded in our entire sort of workflow. So to generate like a, I don't know, 500,000 draws, it's approximately 15-30 minutes. Yeah. So if you have this idea that you complete this exercise and you accidentally misspecified, or you realize that you want to change your prior or something, you don't have to redo this neural network particle filter part. You could just change your prior and rerun this random walk metropolis hastings algorithm. You will lose 15 or 30 minutes. So that might be attractive for certain applications, perhaps for policymakers who realize that there's a deadline and stuff that didn't really work out. Yeah, okay. And this is what we get from our real data little estimation procedure. And one of those charts is for the standard deviation of the labor productivity, this idiosyncratic risk. And although we use like a really standard aggregate data, nothing about cross section, we can still, it it contains some information about, what is the aggregate, what is the idiosyncratic uncertainty of this model, or what the parameters should be. And it's not really that surprising if you think about the plots that we saw for the DSS network output, right? Where we also varied the standard deviation of the labor productivity, and we saw the higher labor productivity meant that the response rate was lower. And now on this kind of calibrated model, or well, estimated model really, where we kind of keep the model parameters of the estimated posterior means, we do a small experiment. So we have a quite large reference, so large enough to push the economy to zero lower bound. And what we see in those two lines, one is with the estimated idiosyncratic risk. The other one is where we basically artificially made it lower. We can see the points that Jesus was making yesterday morning, right? That it really matters for the aggregate dynamics of the economy. We will see that there's a more severe recession in this world where there's more income risk, and inflation will be lower. And also, if you look at the CLV episodes, frequency of those CLV episodes will be higher, and also the length of this CLV episode will be higher. And then we also have exercise which just simulate the data, pretty much what we did in point 2 with the rank, but now for the nonlinear Hank model, where we try to recover like 12 parameters. And this is basically what the neural network-based probability surrogate model kind of gives us, the kind of likelihood functions for different parameter values. This is what it kind of looks like. And we are also using only like 3 time series, so not all the parameters will be pinned down. So we have to help them a little bit with sharper priors, but some of them are quite well pinned down. And that's pretty much it. Just to really drill down. So what we propose in this paper is a novel estimation procedure based on neural networks, and we have 2 key innovations. One we call this extended neural network, and this helps us to avoid this repeated solving of the model. And the second one was to make the likelihood evaluations very fast, and to call it neural network particle filter. And yeah, this framework, I think it's the application here is pretty much focusing on heterogeneous safety models. Of course, you can use it for other macroeconomic models. Similarly, you could use it for also different inverse models if you have something other than estimation in mind. And yeah, thank you.
We have time for a couple of questions. And so have you compared this without estimation results to like Smith and Walker, so the Lucent work, which area? In terms of thinking about this as sort of try to fit all the time series or even cross section of data.
So definitely, we are working on it, and one avenue is more comparisons with what other people are doing. But right now, I don't have anything.
So in terms of results, are there any different estimation results?
Yeah, ideally, I mean like if you have, well, like we haven't done the exercise properly, so I would hesitate to answer this question. Yes.
I think it's a great exercise, and I think it would be very convincing if in your good old econometric tradition, you could show some Monte Carlo exercises where you simulate data and then you try to estimate models and recover, and see how well you recover your B parameters, depending on and then you can say, okay, as a function of the number of observations that you feed in and these kind of issues. And then also, kind of explore what happens if the true data generating process is outside of the parameter range of which you estimate your rate or things like that.
So
I think that it would really give a lot of extra pull power to the argument that you make.
That's definitely something we can do. This is going that direction. What would happen if it's outside? Little bit of this happened here. You may notice that there's probably you might suspect there's a tighter prior on the smart policy shock. And that's basically what happened that, in the data, what we saw from the first estimation was trying to put the standard deviation of monetary policy shock to the very edge, which we didn't like. So we corrected it by introducing more tight prior. But it's kind of indicative. Yeah, you could do the estimation also in a kind of multi-round fashion. So starting off from something like this, and then figuring out that in the next round, for the ones that are well identified, you could shrink the round, or you could extend them into the direction that you saw that there was a problem. So this multi-round inference kind of approach is something we will do probably.
Okay, thank you very much.